All right, let's finish up chapter 39. So we have a few more topics that we want to take a look at here. What we had just done in the earlier hour was to start from the Schrodinger equation, show that the 1s solution that we're looking at is a solution to the Schrodinger equation, and then from the solution evaluate the scaling factor of the wave function and determine what the energy is for the 1s state. So pretty impressive, right? That we can get all of that information from the wave function as a solution to the Schrodinger equation. So what we want to do now, a couple of things that I want to make sure we get a look at before finishing up the chapter. I want to bring back in this idea of the periodic table and how that is predicted from all of the solutions for the Schrodinger equation. And to do that, let's start looking at well, let's take a look at the periodic table. So the periodic table, staring at the periodic table, is a really useful way of kind of organizing all of the results. And so everybody should have a periodic table with them everywhere they go, right? So I've got my periodic table that I carry everywhere. And the shape of the periodic table looks something like this. So you can get to a point where you can just kind of draw the periodic table. Let's see, 1, 2, 3, 4, 5, 6. It turns out that there's about 7, well, there are 7 levels to the periodic table. If we start at the left side, those are elements that are filling S states. So 1, 2, 3, 4, 5, 6, and 7s, those are being filled. And then when we look at the states, the next section over, remember we had talked about taking kind of a standard periodic table and cutting it out so that it's actually more properly represented. And so I'm going to put in the 4F and the 5F. So these are referred to more commonly now as the inner transitions. And then next to those, we will put in and here we are going to have the D's. So 6D, 5D, 4D, 3D. And then finally, at the very end of the periodic table, let's see if we can get this to line up, the P states, 4, 5, 6. So the pattern here, remember we talked about once we start filling a lot of electrons into an atom, once we start moving through the periodic table, it is not the case that everything at level 2 has the same energy, or everything at level 3 or 4 or 5. The levels get shifted around. And so let's see what this turns into. We'll start with the periodic table. So I'm going to get all of these different regions of the periodic table mapped out. Now remember that these are the S states. Those are pairs of elements, 2 elements at a time. These are inner transitions. these are 14 elements at a time. Here are the transition elements, 10 at a time, and then finally groups of 6 over here at the far right of the periodic table. So if we do a count, so here's kind of the way you can keep track of this. If I look at the periodic table, what I find is that on the first row, there are 2 elements. And those 2 elements are over here filling the 1s. So that makes sense, right? We start with the lowest energy states. Those are the ones that get filled first. Those correspond to the elements hydrogen and helium. Now, every time we finish a row and drop to the next row, what that's telling us is that there's a gap in terms of energy. So that's telling us that throughout the periodic table, well, I guess when we're filling the periodic table, there's a gap between the 1s and the 2s states, and it's significant. And that makes an element that has filled both states in the 1s set of states especially stable. So that's the first row. Now if we move on to the next row, what we find is we have a 2 plus 6. We have 2 s-filling elements and 6 p-filling elements. So that's 2 plus 6. Now if we move down to the next row, there is another 2 plus 6. And let me clear out some space here. So I've got a 2, 2 plus 6, 2 plus 6. Now what's missing on this row are the 3 Ds. And so what has happened is this. Let's take a look at hydrogen. And here is hydrogen. We'll say here is level 1 in terms of energy. Here is level 2. Here is level 3. Here's level 4, and we could draw in more, but the basic idea is, what happens then as we move through the periodic table? Well, you go through the periodic table, and what's happening as you go through the periodic table is each time you go to the next element, there's an additional proton in the nucleus. That means there's an additional force drawing the electrons in closer. Every time we bump up the charge in the nucleus, that's going to draw electrons in closer. So what happens is, it's the accordion effect. What you start with is this hydrogen, and as you have more protons in the nucleus, everything gets stretched downwards in terms of energy. So we can start with, remember our 0, we'll say this is 0 energy. It represents ionization. So what happens then, as here we have 1 proton. And over here we'll call these heavy elements. So we're thinking elements farther into the periodic table, and it doesn't take very far to start really boosting the energies. So we've got 1 proton here. We have some number of protons, let's say many protons. Now there's not room on the board. I didn't scale this properly, because it turns out that this lowest energy state gets pulled much, 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 much lower in terms of energy. So what's going to happen with the heavy elements is that, let's say that n equals 1 is, well, it's not to scale. This could actually be hundreds of times lower in energy. We'll do some examples and carry out some calculations to see how low some of these energy states actually drop once we start looking at heavier elements. Now, what happens with all of the S's is they all get pulled down. So we're going to say, here's this accordion effect. I got more protons in the nucleus. It's pulling all of the S states lower in energy. So I'll put the n equals 1 here, and n equals 2 here maybe, and n equals 3 here. Now what the periodic table is telling us is that at least for levels 2 and 3, the P's are similar in energy to the S states. So that says when I look over at what's happening to the, we'll say these are the S, P, D, and F. So here's the S. Now when I look over at the P, so this is 1s, 2s, 3s, well the P's are still similar in energy. And that's, again, observationally, we can look at the periodic table and figure, oh yeah, that must be what's going on. Now, the 3Ds, however, end up more similar to the 4s and the 4p. So, ooh, we do need to get a fourth row in so we can see this. I'll move this up to here. We'll say here's the 4s and the 4p. So when we look at the D states, notice how when we go from 3s to 3p, and then there's a jump to 3d. So 3D's energy is quite different from the 3s and the 3p. In fact, it's so different that it actually becomes more similar in terms of energy with the 4s and the 4p state. So that's what's happening with the periodic table. That's why when we look at the S and the P's, the 4s are on the same level, the 5s are on the same level. But when I look at the D's, they're all shifted down by 1. Now, in some ways, I guess we feel fortunate that that pattern is simple enough that the D states always end up being shifted. They get left behind in this accordion effect. The S states get pulled down the most. The P states are right behind them. Oh, this is 3p. But adding more protons in the nucleus is not as effective at lowering the D states, and we'll see why with that. But in any case, the 3D states, again, are getting left so that they have energies very similar to the 4s. So the 4s and the 3D are actually pretty similar, and that's why those elements, if we look at electron configurations for those elements, that's kind of where electrons get borrowed back and forth. Electrons get borrowed back and forth between the 4s and the 3D. Very same thing happens between the 5s and the 4D. So for 2 rows, there's borrowing taking place here. Then the borrowing gets more complicated. So as we move down to the next rows, what we find is that the F states get left behind by 2 complete steps. So the same kind of effect that we've talked about here, but it reproduces itself with the F states. So what happens then is we end up with a pattern where these fill first, but then as we start putting more electrons in, sometimes S electrons get borrowed back and forth. Now, we're not going to go into a lot of detail. In chemistry classes, they're going to be more clear about all the rules for keeping track of where you expect those electrons to be. Now, in our textbook, we have to check and see if this is a true science textbook, because if it's a true science textbook, there it is. There's a periodic table in it, and it's on a prominent location right at the back. So there's the periodic table, and you can go through this periodic table. Uh-oh, this one needs some scissors too, because these inner transition elements, we have to cut open the periodic table and slip those in like we did right here. All right. But if you look through here, they've got the name of the element, they've got some mass listed, and then at the bottom, in each one of the boxes, they've listed the electron configuration. So that's how important it is for us that to keep track of electron configurations. Now what you find is that for most of the periodic table, the electron configurations follow the kind of the simple rules that we've set up here. Those rules being that if I'm filling an S state, if I'm over here with these elements, I just read down the periodic table and fill these. Same thing with the P elements, there are no exceptions here. Where the exceptions show up are between the inner transitions and the transitions with the S states. Once we're filling these elements, there can be some confusion. But that's okay, you guys don't have to remember this. You guys are expected to be able to recreate kind of this basic periodic table. And let's finish doing this, and then we'll look at some examples of electron configurations and how those are going to be filled. All right. So kind of quickly, let's go through this. So first row, 2 elements. Next 2 rows, 2 plus 6. That's going to give us 8 on each of those rows. Now, if we think of this as cumulative, so here's our cumulative count. The first row of the periodic table is going to stop at element 2. The next one's going to stop at 10, and the next one's going to stop at element 18. Now, these are the noble gases: helium, neon, argon. They were actually inert gases when I was in college, and I'm not sure when they became noble. Noble always feels a little silly to me, but we'll call them that. So helium, neon, argon. Now when we get down to the next 2 rows, what we find is 2 plus 10 plus 6. And 2 plus 10 plus 6 means that on these rows we have a set of S elements, set of D elements, and a set of P elements. Even though their numbers, their principal quantum numbers, N, don't match, they end up on the same row. And so we've got 18 in those 2 rows. And then finally these last 2 rows, 2 plus 14 plus 10 plus 6. 2 plus 14 plus 10 plus 6. So who knew that you could recreate the entire periodic table just from the numbers 2, 6, 10, and 14. 2 plus 6, 2 plus 6, 2 plus 10 plus 6, 2 plus 10 plus 6, 2 plus 14 plus 10 plus 6, 2 plus 14 plus 10 plus 6. Now that leaves these rows at 32 each. And you can tell the chemistry and physics students going around campus because they're reciting that mantra, right? 2 plus 6, 2 plus 6, 2 plus 10 plus 6, 2 plus 10 plus 6. I had to look. 2 plus 14 plus 10 plus 6, 2 plus 4, and that's it, that's the whole periodic table. If we think in terms of the cumulative effect here, then the elements that we're going to have at the end of each row are elements 2, 10, 18. 18 more gives me element number 36, which is probably krypton. 18 more gives me element 54, which is probably xenon. 32 more gives me 86, and that's probably radon. And then there is element 118, which I had written down in my notes. See if I can find those notes right now. It is called oganesson. Oganesson. So another nice feature of the periodic table set up this way is that, researchers have been generating elements beyond uranium since UC Berkeley first generated and isolated neptunium and plutonium back in, I'm going to say, the early 1940s. So if you go up to the old chemistry building, it might be Gilbert Hall. I better check on that. Oh, it's Lewis Hall. I think it's Lewis Hall. If you go into the building, there is, and walk down the corridor, there's a door for one of the rooms, and there's a plaque on the door And it says, in this room were first isolated the first trans-uranium elements, the first elements beyond uranium that we don't know that these ever existed in nature, or they did exist in nature, but they have radioactively decayed, neptunium and plutonium. So kind of that start got, kind of started out right here. Anyway, what's happened, you know, uranium's over here in the 5F region, and what's happened since then, over the past, God, it's going 80 years, right, is that researchers have filled in and identified elements all the way up to oganesson, and that's it. Now, there could be an additional row that shows up, but you know, any additional elements that show up are going to be very short-lived. The oganesson has a lifetime of a fraction of a millisecond. Now that's actually fairly stable, but in any case, for us, we're going to say, hey, that's the whole periodic table, right? Now, so for example, how could we identify or make a prediction, kind of a first order prediction for any particular element that we're given? It's like, okay, you give me an element and I can make an estimate or a prediction as to what its electron configuration will be. So a good example of this would be, I guess, uranium. We could try uranium and see if that works. All right, what's the electron configuration for uranium? And uranium is element number Z92, and we designate different nuclei based on what their number of protons are. They get classified as different elements. And so uranium, the element uranium, or the nucleus uranium, has 92 protons in it. Now, if it's a neutral atom, that means it will draw 92 electrons into these different quantum states. So what I can do then is I can run through these numbers and predict what the electron configuration would be. So we start off with 1s2, 2s2, 2p6, 3s2, 3p6. Now we're down to row 4, and here we have to remember to put in the 3Ds. Now we got to get down to element number 92, so I'm filling all the rows down to here. I'm going to fill rows all the way to radon. That's my plan. And then beyond radon, I have to come down to this last row and fill in 6 elements here. So I'm thinking uranium's going to be right in there somewhere. Uranium's going to be a 5F element, and we're getting there. So let's keep track of the rows. We don't want this to become too confusing. That was row number 1. That's row number 2. That's row number 3. This is row number 4. Once we get down to rows 5 and 6, things are going to get more complicated. Now for rows 5 and 6, we're going to have to include the F states. And those are going to... Oh, I'm sorry, we've got one more of these. I take that back. We've got one more. 5s is going to go with 4d10 and 5p6. So we had one more of those rows that had 3 suborbital sets of quantum states. Now we're down into the F states, and that first row in the Fs, 6s2, 4f, 14, 5d10, 6p, 6. All right. We're not quite finished, but what we are through is we're through the first 6 rows. Okay. And then our prediction for the last row would be, I need 6 more electrons. So our prediction is 7s2. So I'll put 2 electrons in these 2 states, and then I'll move over into the 5f. And I need 4 of those. So we'll say 5f4. Now, everything except the last row are considered to be core electrons. When we're looking at chemical reactions and how compounds form, the core electrons are just not going to be involved in the chemical bonding. We'll see some exceptions to that, but for the most part, these core electrons can be thought of as just a bunch of electrons that have been, we took away our diagram here, but they've been brought very close into the nucleus. They're filling in entire shell regions, and that means that the core electrons are going to be very, very stable. When we fill a row, we have a set of electron states now that are exceptionally stable. It's going to be very difficult to bring one of those electrons out and have it participate in chemical bonding. So what happens is, we have core electrons, and we have bonding, or what we call valence electrons. So it says that in uranium, we have probably 6 electrons, potentially, that could form chemical bonds. Doesn't mean that always all 6 of these are going to get involved, but very commonly that could be the case. So a simpler way, that was a lot of stuff to write down. A simpler way to write this for uranium is we use brackets, and we look at the completion of row 6, and we say, look, here's a shortcut method. What we can do is say, all right, all of uranium's core electrons are equivalent to the electron structure in radon. So we can identify the electron structure in radon. That takes care of the first 86 electrons. And then all we have to write is this: 7s2, 5f14. So for us, that's kind of our rough prediction. Now, what we had said earlier is when we make these kind of predictions based on going through our standard diagram for a periodic table, we're always going to get everything in the S columns correct. We're going to get everything in the P columns correct. But whenever we're in the inner transitions or the transitions, it could be that an electron or two have been swapped back and forth. So what we can do is we can check with the textbook. Now, we're just doing this to see how our prediction compares. And it says that researchers have identified that in uranium, the electron structure is actually a little bit different. Let me write it in the order we've written it. It is 7s2. But instead of 5f4, it's 5f3, 6d1. So this was just based on that, following that simple set of rules, and here's what researchers have actually just found out. And all it's saying is that one of the electrons got moved to an F state or into a D state rather than being in an F state. And it's not a big deal, okay? That's kind of a standard sort of exception that we see when we're working with these electron configurations, okay? So, questions on any of that? So you'll see some homework problems on this too. Now, it's always, once in your life it's good, or twice, or maybe 3 times. It's good to take one of these really heavy elements and write out its electron configuration. And what you're doing is you're kind of reinforcing this pattern that we showed for the periodic table. But once you've done that a few times, you're thinking, okay, I get it, I know what the pattern is, and then go back and start using these abbreviations. right? So complete the core by just writing down one of those electron configurations, and then just focus on the valence electrons or the bonding electrons. Okay. All right, now the energies, what we've said is that the energies of these states get complicated. So let's take a look at examples of a couple of ways that we can still approximate the energies that we have for these electron states in heavy elements. So let's take a look at this. Now, first of all, let's go back and ask about S states and what the wave functions of S states look like. Now, we said that the S states are spherically symmetric. So the S states, you can draw them as kind of a sphere. Now, what does happen with the S states is that they can have what are called nodes. Where the probability actually does drop to 0. So in the 2s state, for example, look at some of these more complicated quantum states. Everything is still spherically symmetric, but the probability is split into different regions. Now the outer region always exponentially tails off as we get farther and farther away. But this inner region actually is a region of probability separated by a node, a region where the wave function goes to 0. And so if we look at the 2s state, for example, in terms of, we'll look at that probability as a function of radius. What we find is that we get these nodes are regions where the probability goes to 0. And that node is spherical in shape. So that's kind of what a 2s state would look like. Now what are the p states and the d states look like? And let's take a look at the p states. I think that's enough to see where we're going with this. If we look at the two p states, now there's going to be an m sub l is equal to +1. Here, L is equal to 2. There's going to be an m sub L, or I'm sorry, L is equal to 1. M sub L is equal to 0, and M sub L is equal to -1. And we can take a look at each one of the wave functions and ask what that looks like. So let's draw our picture here. So here's our z-axis, and then here is the xy plane. Now, what we find is this. The wave functions, again, what we're looking at are wave functions squared. And now we're going to put the angular dependence back in. When we look at the wave functions for these two p states, what we have are donut shapes. Or I guess a more proper math term would be something like a torus. So what happens is we get a set of states that, well, they're kind of donut shapes, right? So it's kind of the probability region, most of the probability is within a donut-shaped region, and we're going to arbitrarily place that with the z-axis. Now, the states that have that appearance to them, those are the m sub l equals +1, and the m sub l is equal -1. This is kind of interesting in that these two distinct quantum states exactly overlap with each other. When we carry out their probability distribution, the probability distributions match exactly for these two states. And you go, well, what sets them apart then? And in order to see what sets these apart, so there's a state where the m sub l is -1, there is a wave function where the m sub l is +1. And if we look at the time dependence on those, the pattern of phases circulates in one direction for +1. It's in what we would call the positive direction mathematically. And then for the -1 state, it circulates in the other direction. And that's kind of the closest we get to saying that there really is something circulating in these wave functions that describe the electrons inside atoms. So orbital angular momentum comes down to not the probability level, but the level of just the wave function before we've squared it. And the wave function describes this donut-shaped pattern, again, circulating in one direction for +1, circulating the other way for -1. So that's kind of interesting, that there is this rotation effect, at least at the level of the wave function. Once we modulus square, then the probabilities look exactly the same for both. Okay? So you can't tell one from the other. And then there's got to be a third state. So we said that takes care of the m sub l +1 and the m sub l -1. What does a zero state look like? And it fills in the remaining area. So this is like lobes above and below the xy plane. So here is the m sub l equals 0 state and what its wave function looks like. Now, when you take the probability functions of all three of these and add them together, what they do is they fill the space uniformly in a spherically symmetric fashion. Let's say that. It's not uniform, but it becomes spherically symmetric so that by adding together all the different angular momentum states, you get something that's a sphere. Okay. So that's kind of interesting that, well, let's go back to the S state. If I walk around this electron wave function, I don't see any variation at all as I walk around in an angle. But for the states that do have angular momentum, as I walk around through the z-axis, and I do see variations, right? I go from high probability to low, back up to high probability, down to low, back up to high probability, and that's kind of the basis of orbital angular momentum. It depends on what the shapes are like. So this is only one unit of angular momentum. When we go up to other states with more units of angular momentum in them, the pictures get more complicated. These are all in your book. You can see them online. But if you go up to D states, for example, D states are going to have many more lobes of probability than what we've seen here. Okay, but this gives us a good idea as to what's going on. Now, what this plays into is when we were saying, you know, here's the 1s state, and here's the 2s state, and here is the 2p state, and here is 3s, and here is 3p, here is 4s, and here is 4p. Well, the 3d states got left behind in terms of energy. As we add more and more protons in the nucleus, all of these states are getting drawn down, but the d states do not get drawn down. They don't get pulled in as much, and that's because of their more complicated shape. The shapes that are more similar to spherical symmetry get pulled lowest in energy. The ones, these p states, the two p states, get pulled almost as much, but as this pattern of wave functions gets more complicated, they just don't get drawn into the nucleus as much. as we begin adding more protons. So these different shapes are kind of the basis for the pattern we see in the periodic table. Okay. So let's take a look at an example. We don't want to run out of time here. We do want to be able to look at an example of how this is working. And I think what I want to do is I'm going to borrow some information from problem 41. Which looks like a good problem to look at to see how this is working. So in problem 41, it says this. It says that estimate the wavelength for photons generated in an N2 to N1 transition in iron. So let's write that down. Now we're looking at the element iron, and in the element iron, Z is equal to 26. That's 26 protons. So what are the energies going to be like for these different states, say the 1s and the 2p and 2s states? So let's take a look at this. What we've got in iron, I'll draw an energy diagram here. So we'll say here is the 1s state. And here is, we'll say there's a 2s and a 2p states here, and these are kind of similar in energy. What they want to know is, if we take an electron, let's say we have an electron in a 2p state, and it drops into the 1s state. Well, that's a lot of energy. It looks like it took its time. I want to make it look like it was more directed. There we go. So let's say that we have an electron that drops from a 2p state into a 1s state. That's going to really reduce the energy of that electron. And what will happen then is that we'll get a photon generated from this. So we've seen this before. We saw this in elements like hydrogen, maybe helium. But now we're going quite a ways into the periodic table. So what we can say is the energy of this photon is equal to the energy of an electron on level 2 minus the energy of an electron on level 1. Now, we can't use the formula for hydrogen. That's not going to work. We've got to come up with some way to approximate the energies. Now, it turns out that specifically for these state 2 to state 1 transitions, there is an estimate approach that works really well. And that is that the energy of state 1 is well represented by minus 13.6 eV times what we call Z effective. Now, Z effective says this. It says that if I'm an electron in this n equals 1 state, there's not much between the nucleus and me. So I'm feeling almost the full effect, but not quite. I'm not quite feeling the full effect of the nucleus. And so what we're going to say is that the Z effective then is equal to Z minus 1. What we do is we just subtract one of the electron effects. Now, let's step back and see why this maybe is justified. Before the electron can drop into state 1s, an electron has to be removed. If there's already a pair of electrons in that state, an additional electron can't drop down. So the first thing we've got to do in order to make this transition happen is we've got to take one of the electrons that was already there and remove it. So let's say there were a couple of electrons here. We collide something with this iron and remove an electron. Now, the way this typically works this is like an X-ray machine. So what we can do is we can take a beam of electrons. Let's say we have a thin sheet of iron, and we've got a beam of high energy electrons that we've accelerated through an electric field. So we can't really send photons in because, well, it's an X-ray machine. We're trying to generate the high energy photons. But we can control electrons pretty readily. So we can build devices that can accelerate electrons to very high energies. We can direct those beams of electrons towards a piece of anything, a piece of iron in this case. And what happens is those high energy electrons will remove electrons from some of the lower energy states within the iron. So these high energy electrons come in, they disrupt some of these electrons in the iron, and some of those are going to be in the lowest energy state. So that's how we open up a quantum state. Now, once I've opened up a quantum state like that, then one of these electrons, making its drop into that state, between that electron and the nucleus is just one electron. And that's kind of our justification for using Z effective for this electron making a transition. We reduce the effect of the nucleus by 1. And that's because there's already an electron between the electron at level 2 and the nucleus. Okay, so this is what we're going to do. It gives us an estimate. We estimate energy state 2 and energy state 1 using the same formulas, except we're going to adjust for the energy level that we're on. So this was energy level 1, this is energy level 2. And the 13.6 is what we would see from hydrogen itself. And then the Z squared is actually something that derives back from the Schrodinger equation. So we end up with formulas that look like this. Here is the Z effective. We're going to use the same Z effective for both of these. And that says that the energy of the photon is going to be the difference between these two. Now, before we carry that out, I actually want to go back and just calculate the values that we have up here. Plugging in all those numbers that we've talked about here says that energy state 1 is at minus 8,500 EV, and energy state 2 is at minus 2,125. Wow. So in hydrogen, those 1s electrons had a binding energy of 13.6. But notice what happens as you move through the periodic table. Those energies increase by a factor of Z squared. So even iron's not terribly far into the periodic table. You know, that's only element number 26. But even in iron, what we're seeing is the binding energy for individual electrons in the 1s state, 8,500 EV, state number 2, 2,125 EV. That's a lot of energy. So these are really high energy transitions. A transition from level 2 to 1 in hydrogen would be 10 EV. You know, it would be barely ultraviolet. But once we create these transitions in heavier elements, then the photons that are being produced are really energetic. They're going to be in the X-ray region. So what we can do from this then is take the difference between these two energies, and the photon energy that we calculate from this, 6,375 EV. Okay, that's a lot of energy. That's an X-ray. So once you get past, you know, several hundred or maybe 1,000 eV, probably several hundred, you're into the X-ray region. You start to generate photons that have really high levels of energy. So that's what happens. And since the electron coming in has momentum in this direction, the particles coming out the other side are mostly collimated into the forward direction, and that gives us an X-ray machine. So we can send in a beam of electrons into iron or cobalt or zinc or whatever, remove some of these electrons, and then create these really high energy photons. So that's really high energy. Now, energy, I always feel like energy is the important quantity to keep track of here, but we could go and look at the wavelength. So the wavelength of the photon that we just generated is given by hc over the energy. That's going to be 1240 eV divided by 6375. Ooh, this is eV, let me change this. eV nanometers. And so the wavelength for this worked out to be 0.195 nanometer, which I'm going to adjust into picometers. Okay, so these wavelengths are getting down to a fraction of a nanometer, and those are in the X-ray range. Again, conceptually, I think it's easiest to think in terms of energy. It's hard to think in terms of wavelength, and wavelength's always an extra step in these calculations. All right, I think that is pretty much what we wanted to make sure that we got through for the day. Trying to see if there's anything else that we need to look at. Let me say this also. There's one of the homework problems, probably a bit beyond what we're really, the last problem. So homework. This is chapter 39, and the number on that, the last one on 39, is problem number 47. You can look at this section if you want to, but don't worry. It's involved with more complicated angular momentum, and if we get the basics down in all of the previous sections, we'll be doing good. So I think one last check. Let me just make sure we're good for the week, because that's really what this is coming down to. Yeah. So the plan then is take a look through this chapter, look at all the homework problems. Let me know if you guys have questions, and we'll maybe take a look at some of these problems in the next lecture, but we're ready to move on into chapter 40. All right.